another day, another vlog. It's your girl Ella. So come spend this 2 days with me, which means because this is two days vlog in one video. So
Good evening, everyone. Please, the meeting will begin shortly. And as always, we allow for our bosses, princesses, and princes to join when they are ready. So please bear with it. And yeah, sorry. Good evening once again, everyone. So I think we've allowed enough time, so we can start our meeting. Welcome once again to another session of the making class. Today's session was slot a story for DCIT 203. However, the tutor for some unprecedented reasons cannot make it tonight. So I am being standing in his seat and I'm taking this session. Hopefully at another time you'll make it up for the lost time. Then again, the session is not being lost as we are still gaining, but just from another side. So we'll continue with the remaining parts of the session. Chapter 4. Chapter 4, that's the last part of chapter 4 of the Stallings manual. So let's get right into it. Before we do, I would like us to recap what we learned yesterday using some objective questions and then try to answer the questions to assess what you have studied in the lesson. Okay. Okay. Right. So question 1, if you know the answer, just raise your hand and then go. It says, which statement best describes temporal locality? Which statement best describes temporal locality? A, accessing nearby memory locations, or B, reaccessing the same memory location within a short time, accessing memory randomly, or D, increasing memory size. Yes, Mr. Joshua.
Please B. We are accessing the same memory location within a short time.
Reaccessing the same memory location at the same time within a short time. Okay, that's what Mr. Joshua thinks. What about the rest of us? Do we agree with him? Or if you agree with him, show it a thumbs up. Or if you don't, raise your hand and then please choose the right answer. Because he may be wrong, actually. Right. Mr. Ebenezer agrees. Okay, so let's see what the correct answer to this is. Right, so then the answer is B. It says temporal locality means if a memory location is accessed, it is likely to be accessed again soon. So, example in loop counters. Question 2, which statement best describes spatial locality? Accessing memory far apart, repeatedly accessing one address, accessing nearby memory locations, increasing clock speed.
Yeah, hello,
Yes. Yeah, Mr. Joshua.
Please, is my answer correct?
Yes, please, it's correct. Sorry,
Okay.
this is the answer. So B.
Oh,
Okay, and working temporal locality means if a memory location is accessed, it is likely to be accessed again. So it says correct.
All right, thank you.
Yeah. Yes, on to the next question. Which statement best describes spatial locality? Which statement best describes spatial locality? So please, to those who were present in the class yesterday, this is your opportunity to see if you were able to grasp the concepts or they went over your head. Okay, let me call some people and maybe they'd like to try. Yes, Mr. Venix. Mr. Emmanuel, sorry. Please, Venix. Mr. Emmanuel.
Yes, I'll like
Yeah.
number A.
It's A. Accessing memory far apart. All right, okay. Mr. Ebenezer Nyakon, what about you? What do you think?
Okay. So I also think C, accessing
C,
nearby
okay.
memory locations.
All right, he says accessing nearby memory locations. Okay, that's good. Madam Daniela, please, which one do you think is the answer?
Yeah, I also think it's C, accessing nearby
Okay,
memory
memory
locations.
locations. Okay, what about you, Mr. Antivida? C, okay, and Mr. Eric Aban or Aban, yes?
Yeah, it's C, please.
It's C. So let's see that. And the correct answer truly is C. We learned that in spatial locality, memory locations are fetched together. If a data is fetched from a memory, if a memory space is addressed, then that memory space is likely to be addressed with other closer memory spaces. They are all fetched together. This makes it easier for the CPU to run faster. So spatial locality means if one memory location is accessed, nearby locations are likely to be accessed soon. And it's used in the case of arrays. So look for temporal and then spatial in arrays. In the memory hierarchy, which is the fastest? So which of the memory is the fastest? Which of the memory is the fastest? I can see Mr. Ebenezer, your hand is already up. Yes. Which of the
So
memory
is a cache.
is the cache? Cache memory is the fastest. Do we agree? Okay, antivirus says cache. That is correct. So cache memory is the closest to the CPU and it has the lowest access time. Therefore, it's the fastest. AMAT is calculated using this. So average memory access time is calculating using which one? Is it hit time times miss rate? Yes, Mr. Joshua.
Yeah, hit time plus miss rate times miss penalty.
Exactly. So hit time plus miss rate times hit penalty. So do we all agree to that? Show it a thumbs. Let's move fast.
Yes.
All right. Okay. Let's proceed. So yes, you're right. Let's move on. Given hit time to be 2 nanoseconds, miss rate to be 0.05, miss penalty to be 40 nanoseconds. What's the average memory access time here? Let's work fast. Yes, Mr. Joshua.
I'm not with the book right now, but I created it in my mind, so I don't know whether it's correct.
Yeah.
8
Yes,
nanoseconds.
mass caller. 8 nanoseconds. So okay. Mr. Joshua believes it's 8. Right. He says it's without a book, so even if it's wrong, we should just let it slide because it's using the yes, Auntie Abigail.
I think it's 4.
Okay, she also says it's 4. Yes,
I
is
have
there
4.
anyone else that you also had 4? Okay, right.
It's 4.
Anti-Vida. So Mr. Joshua, I think there's a little more that you have to do. Let's see what's happening here. So you know the formula that the AMAT is equal to the hit time, right? And then we add that to the products of the miss rates. And then the products of miss rates and what's the penalty. If we combine all these together, the hit time is 2. Our miss rate is 0.05. That means 5%, right? 0.05. And then we multiply that by 40 nanoseconds, so times 40. What this means is we have 5 over 100 times 40. That multiplies and simplifies to the value 2, because 5 times 40 is 200. We jump the point back 2 times, we are left with 2. And then 2 plus 2 gives us 4 nanoseconds. So the correct answer is actually A, which is 4 nanoseconds. 4 nanoseconds. All right. So then, yes, the correct answer is 4 nanoseconds. Let's proceed. If miss rate increases while hit time remains constant, what happens to the average memory access time? If the miss rate increases but the hit time remains constant, does the average memory access time increase or decrease? Let's apply some creativity to our thinking. So it says the miss rate increases. It means the chances that we will not find the value inside the cache increases. Yes, please, what's your answer? It's B. Okay, she says the correct answer is B. So Vida thinks it's B. Yes, let's vote. How many of us? Where do we stand? Where do we stand? Okay, everyone else doesn't know the answer, but Vida thinks it's B. Right, so let's see what the correct answer to this is. So increasing miss rate increases the 10. Therefore, the average memory access time also increases. What this means is that when the miss rate is high, it means the chances that we'll be accessing memory outside the cache is also very high. And then in this case, miss rate increases, penalty times miss rate gives a greater value. Combine that with the constant hit rates, And then we get something that is a larger average memory access time than what you would have gotten if there was no increment in mesh rate. So it increases, it means the performance reduces. All right, so we've come to the end of the questions here. If you had any questions tied to our previous session, feel free to ask before we move on to what today has for us. While you do that, I'll also be preparing a question for you to tackle right now. Yes, Mr. Nyako Ebenezer, you may speak.
Okay, so please, my question is on the last one. Can we use variables or figures to explain the answer?
So the question that came previously, you're talking about this question. Let me see. This one right here.
Yes, please.
Can you use variables? Yes. So you may say, let's this be equal to that, let this be equal to that, and you explain using that. Now, provided these two remain constant, the value here increases due to blah 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 blah. And if you want to explain even further, perhaps you might consider doing a small example with a working. It depends on the question's mark size. So that will depend on that. But for a question as basic as this one,
so,
where it's just
so it means that only the hit time is going to remain constant. The miss penalty is going to change, right?
No, the miss penalty also stays the same.
The same. Oh,
yeah.
Okay.
But then the miss rate actually increases. So the increment in miss rates means the product of the miss penalty and the miss rates is going to give a bigger product, right? That larger product combined with the constant, what do we call it, hit rate. So let's say the hit rate was standing at 2. We increased the miss rates from something like 0.05 to 0.5. That increment will mean that if the miss penalty used to stand at 10, the product of 0.05 and 10 would have given us 0.5. But since we have now increased the miss rate to 0.5, then the product now gives us, instead of the 10, it gives us what? Something like, let me see, 0.5 times 1. It gives us 5 times 10. It gives us 5, right? Sorry. So I combine 5 with the initial one, I get a higher value as compared to what it would have been had the miss rates not changed. There might not be much of a difference. If the miss rates increase, then also the hit rates also increased. If they both increased at the same margin, then there wouldn't have been much of a difference. Yes.
Yeah,
but seeing as one increase.
Yeah.
Yes, sir. Yes,
Thank
sir.
you very much.
All right. So I was saying I'll prepare a question for you. So here is the question I have for you. Suppose you are given a memory space and you are told that the access time for the level 2 cache is 40 nanoseconds. And the penalty for addressing RAM, so this is level 2 cache access time, by the way. The penalty for addressing RAM stands at 70 nanoseconds. And you are told that level 2 has a miss rate of 15%. At the same time, we are told that level 1 has a hit rate. Level 1 has a hit rate of, let's give it, it has a hit time of 20 nanoseconds, like this. Good. I want you to calculate the miss rates for the level 1 cache. Given these parameters, we know that level 2 has an access time of 40 nanoseconds. The penalty for visiting RAM, let me put that here, RAM penalty is equal to 70 nanoseconds. The level 2 cache has a miss rate of 15%, and then level 1 cache has a hit rate of, or a hit time of 20 nanoseconds. And you are told that we are to find the miss rate for level 1 cache. Can you manipulate the formulas from yesterday to calculate these things? Remember that the access time for level 2 has already been given, so you don't need to compute that separately.
Yeah, hello, Mr. Prince. Please, I want
Yes,
to
madam.
start. Yeah. Please, are we solving for miss penalty alone, and then we come to L1 miss penalty alone and L1 rate miss rate too, like different.
No, we are only solving for the level 1 miss rates.
Okay.
Yeah.
Thank you.
So to clarify a little something here, there is only a penalty for level 1 if it is visiting a particular lower storage to access data. But in this case, the storage it is visiting will be level 2. Therefore, the penalty will be the access time for level 2 in this case. So it's already given. Level 2 will also visit RAM to get values. Then the penalty for level 2 will be the access time of RAM. Anyako. Yes, sorry.
Okay, so I had 28%.
So for his miss rate, Mr. Nyako has managed to get 28%. Okay, that's a good start. Let's see. Yes, let's see what else comes. He might be right.
So for the AMAT, what are we getting? The AM18. What's the number there?
Hey, I didn't give you the average memory access time.
Yeah.
Sorry. You see, I didn't give you that parameter. I did. Sorry. I didn't notice it. Sorry. So let's give an average memory access time, okay?
And somebody has gotten
Then
that.
I have to restart.
Right. And 0.99 approximately 27.3. Yeah, hello, please. My answer is 27.3.
You've already found the answer, but I just put it there. Okay.
Yeah, but I was solving before I asked the.
Oh, excellent. So you said your answer was what?
27.3. 0.99,
27.
so approximately 0.3.
So 27.299.
0.99.
So then 28.
Yeah, sorry, 28.
All right. Oh, okay. Then Mr. Nyako, looks like
And
despite all that, you are still standing on business. So okay,
Yeah,
let's see.
my magic did work.
I can see. How is this possible? Okay, let's see that. Perhaps there is something that's clear that we are not noticing. Okay. Yes, are any of us still working, or should we just proceed with the working? We have to dive into the next lesson is actually short. It covers the remaining of the what do we call it? So it's not much. Yeah. Okay, let's go ahead and work it. Yes, let's go ahead and work it. So the formula for this one is that we take always hit time for the desired memory space that we are using. In this case, is the level 1 cache. And then we combine that with the miss rates for that very same memory address. And that's the very same memory space, which is still the level 1. And then we multiply that value with the access time of the memory it reference, or the one it references. So then this will be the access time for level 2. Normally we'll compute that access time, but in this question it was already given. This means the value for the RAM access time becomes useless. It was just a dummy variable that was given to mislead you. If you fell for it, then it's bad. So then this formula is the AM80 formula, and the AM80 has been given to be 30 nanoseconds, right? So let me clear some space on my screen, and then we use it wisely. Please, you have to give me the parameters also. I'm cleaning. Am I good to clean? Okay, hopefully I am. Right. Okay, so the level 1 hit time is 20 nanoseconds. So our average memory access time, which is 30, is equal to the 20 nanoseconds plus the product of the miss rates, which we do not know. So let's use X. So let's let miss rates be equal to X, okay? So you always show them such variable address and variable assignments. So X times the access time for level 2. What was the access time for level 2? Please remind me. People, access time for level 2 that use. It was 20,
40.
40, okay. So 40 nanoseconds.
It was 40.
It was 40. So we have 30 nanoseconds is equal to 20 nanoseconds plus X times 40 nanoseconds. So we do our brackets first. So that gives us 40X plus 20 is equal to 30, like this. So I'm just writing backwards, okay? It's still the same thing. And please, I'm not very good with my keyboard and all that. Sorry, with my pointer, so bear with me. Right. So then if we group like terms, we have 30 minus 20 is equal to 40x, right? And then 30 minus 20 gives us 10, and then it's equal to 40x. So in order to get our rates, we need the x to stand alone. So we divide both sides by 40 so that we can eliminate the variable that is attached to the x. And it's looking like all the answers were wrong, okay? So 40 takes out 40, and 10 goes here 1 and goes here 4, right? And that leaves us with 1 over 4, which is equivalent to 0 0.25. So 0 0.25, which is the same as 25%. So the answers, though they may seem close, they are still wrong. In maths, we say a close answer is a wrong answer, right? So this is it. It is wrong. So 25% is the correct one. So I don't know, I'm sure you fell for the RAM value, right? Was it the RAM that got you?
Yes, yes.
So always be on the lookout, okay? I don't know how tricky the questions are or will be, but I like to always put a little spice in the questions I originally set. So at least it means you know what you are doing, right? It's just you are aware of where your mistakes are. So we are making progress. That's very good. Thank you for your efforts. Let's discuss the remaining of
please, I have a question.
Go ahead, boss.
It's a request, though.
Yeah.
Can you please give us one example on this one so that we try again?
Hey,
for better understanding.
837. Do you all agree with that? Time ago. I can give you, don't worry. 837. How about it? Do you agree? Okay. Yeah, okay. Everybody agrees. So let's just do that, chat. So let me give you some parameters and let's use it again. When we fall, Jesus, and we and then they has chapter 4.4 then we'll stop. We'll have to stop midway. Don't worry, it was not my session. So we being able to use it alone makes it so that it puts us ahead. So you don't worry. We still made good use of the time. Understand it. Right. So this time I'm going to change the questions a little and I'll still put a tricky spice in there. Or like you will never know. So check. Be on the lookout. So we have level 1. Level 1 miss rates. And then it is 50%. And then we have level 2 miss rates. That's 12%. We've got a RAM penalty. Let's put that at Let's see. And then we also have okay, let's see. What else can we include here? So we have the miss rates for this guy. We have the penalty. And then we can include our hit time for level 2, by the way. Mm-hmm. 2 nanoseconds, okay? And also, level 2 penalty. Some values here will be redundant, they are useless, so figure them out. So your main objective at this time, let me include the average memory access time. Your main objective this time is to figure out what your level 1, what do we call it, hit time is. So we are figuring out your level 1 hit time. So apply your creativity again, manipulate the formula, and then figure out what the level 1 hit time is. The level 1 miss rate has been given here is 50%. Level 2 miss rate has been given here is 12%. The RAM penalty is 13 nanoseconds. The hit time for level 2 is 2 nanoseconds. Also, let me include level 1's hit time. Okay, we are finding level 1's hit time. I almost messed up. So yes, everyone, attempt this. Yes, Mr. Benix.
Yes, I don't know if it's me, but like said, you didn't give us access time for level 2.
I did not give you level 2 access time. Yes, you are going to have to figure that out. So you see, in the previous question, it was given, right? Yes. But in this question, it has not been given. So in this question, you figure out level 2 access time, and then use the level 2 access time to figure out the level 1 hit time by manipulating the formula. Yeah. You need further clarification on that, or does that make it clear, Mr. Venix? If you need it, don't worry, I'll give you further clarification if you need it. Mr. Eben, you want to speak?
No.
Oh, okay, all right. Remember, one value here is a dummy value, okay? It is not even a correct value. So compute its correct form and use it in your calculation. Okay, it's 8:46. So in the next 2 minutes, we work this one because Charlie time now swinging.
Okay, so I had 20 22.4 nanoseconds.
22.4 nanoseconds. Okay, let's see that. So here's access time is 22.4 nanoseconds. Rounded to the nearest whole number, that's 22 nanoseconds. Okay, let's see. So that's Mr. Nyafon. Anybody else with any different answer? Or do you all agree with his answer? And the rest, do we agree that we proceed with the calculation, or should I wait on you because you are very close to your answer? We have to move with time. So the 8:48, it's 8:48. So as I said, let's just dive right into it, okay? So let's see what is happening here. Please keep the parameters in mind. Let's find out what is needed and what is not. For this question, we need to first calculate level 2 access time. However, the level 2 access time has already been given, but it might not be correct. Remember that the access time for level 2 will become the penalty for taking values from level 2 into level 1. But maybe this parameter might be wrong. The value here assigned to that parameter might be wrong. That is why you have other information to verify. So what we are going to do is we're going to verify that information. And then we're going to do that by calculating or actually calculating the level 2 access time. So according to what we know, in order to calculate the access time for level 2, we take the level 2 hit time, which has been given to us to be 2 nanoseconds. And we add that to the level 2 miss rates. The level 2 miss rate has been given to be 12%, so that's 0.12. And then we multiply that. This is a 2, by the way. And then we multiply that by the penalty for addressing or taking values from RAM, since it references RAM. So then the RAM penalty is 13 nanoseconds. So times 13 nanoseconds. So 0.12 times 13, what does that give us? So please, what's 12 times 13? If you have a calculator, find that for me. So 12 is 144, right? So 156. So 156, that's 1.56. 1.56. 0.56. Is this computation right? 0.12 times times 13. Is it 1.56?
Yes, it's right.
Yes, good. So we add that to 2 and we get 3.56. So it means the average memory access time for the access time, yes, for level 2 cache is 3.5 nanoseconds, and that will be equivalent to the actual penalty for level 1 referencing it. This means the value here, the dummy value that I gave was the level 2 penalty in this question, so it is wrong. Now that we have confirmed that, we can use it to compute the level 1 hit time. According to the formula we know for hit time, let me clean some of these things from the screen. The formula for hit time of level 1 is inside the average memory access time formula. So we just use that and then we manipulate it so that we can get our answer. So average memory access time, which is 10 seconds. So I'll not write the formula. I'm just putting the parameters, the substitution. 10 seconds is equal to level 1 hit rate. We do not know that. So let's represent the level 1 hit rate with an X like this. So then it's equal to X plus hit time, X into brackets level 1 miss rate. So what was our level 1 miss rate? Was it given? The 1 miss rate was given to be 50%. So 0.5 times, and since level 2 is the memory that we will be referencing for value because it's inclusive in this stage, the access penalty is going to be from level 2 success time, which is 3.5. So 0.5 times 3.5, like so. So 5 times 35, what does it give us? So what does the 0.5 times 5 give us? So 5, 25, 5 remainder 2. 5, 3, 15 plus 2 is 17. So 175. Jump the point back 2 times, and that gives us 1.75. Am I correct?
Yeah, you are right.
Yes. So we have plus 1. So let me clear some space here. So good. Let me go this way. So we have x plus 1.75. Please, I don't have a calculator with me now, so please you can verify the answers as I am computing it. 10. My mind can just go in circles right now and I'll be saying some random things. So, okay, then we group like 10. So our x is now equal to 10 minus 1.75. 75. And then if I subtract this, right, 10 minus 1 gives me 9. And then 9 minus 7, 0.75 will give me what? 8.25. So the correct answer, x, is equal to, yes, 8.25. Ish. We are working on thin ice here on both accounts. We got them wrong both times. I believe you are working with understanding, but there are a few things. It's because of the tricks I'm putting in the questions, right? Yeah, that is what is getting you. I'm sorry. I'm sorry. But then if we do not tighten the questions like this and I make them too easy, you might end up coming across questions that are logically challenging. And then it will be as if, you were being fed all this while, but you were never taught to feed yourself. So let me strengthen your brain with the harder ones so that if you meet the questions and they are simpler, you will take them very easily. So Mr. Venix, the access time that you were looking for, it was actually given already, but it was wrong. And it was a dummy value. So if you compute the actual access time, this is what you get. So then when you were asking about level 2 access time, according to yesterday's lesson, you use the access time as the penalty in the next. Yes, Mr. Emmanuel.
I said I solved for the first time. I got it correct, but my mistake was the miss rates. I forgot to convert it to 0.5. I was really confused.
Okay. So you were using 12 actually. For the percent, you were using 12. Is that right?
Oh, no, I was using like the 0.5, but I did it at 50. I forgot to turn it to 0.5.
Oh, okay. Okay. I see. 50. So the next time, check that, Charlie. That's dangerous. So you could have done them 50 over 100 or 50, 0.5, same situation. Okay, but despite the fact that we are getting it wrong, do we understand what is happening? It's the dummy values that are confusing us, but do we understand? Please show with your terms. Do we understand what is truly happening here? Okay, Mr. Nyako understands what is happening. Auntie Vida shows no reaction. Auntie Daniela shows no reaction. Mr. Akwanda shows no reaction. It means, listen, I eat beans. Oh, okay. Our time is up, so I cannot take you through the next lesson. But here's something I can do for compensation. The remaining 5 minutes, I'm going to use it to recap what we learned concerning the inclusive access time and then the exclusive memory access time too. So then maybe that will make the concepts clearer to you. Okay. Don't worry, Charlie. We all forget things sometimes. It's very normal. So let me pull up that lesson quickly. That was performance modeling and AMAT calculations. Good. So this is where it was. We learned yesterday that having separate memory spaces and you are Steve, and then there can be exclusive address or exclusive memory usage. Inclusive memory usage occurs when values that are this time is a penalty. We were using the table in the library analogy, and we said when you're seated at a table,
Hello. Can anyone hear me? I can't hear you.
Your line was breaking.
Is it teaching?
No, I think he's having a problem with his network.
Okay, guys, how about now? Can you hear me clearly?
Yeah, you can hear you.
Okay, sorry, and I don't know what leads to that, but I can hear you very clearly when you say you can't hear me, but for some reason I am speaking and then I'm inaudible, but I can hear you very clearly. My mic is unmuted, data works on every other channel, WhatsApp, whatever, but for some reason, okay, we never know. I was explaining the concept from yesterday so that we understand it better, and I was saying that right. I was saying that if we take the addressing from memory, or when we take moving data from one memory level to another, the time or the amount of time that it will take to travel, that's all, to move that data from the memory space I to II, that becomes a penalty that I has to pay. The reason is simple. Go back to the library analogy. When you are seated at a table and there is a book next to you, and then the shelves that the other books are stacked on are 5 minutes away, if a book is already on your table, all you have to do is reach out and take it. That's almost instantaneous. So then the only problem you are facing will be the distance between your hand and then the book on the table. And that will just be a small amount of time, right? However, if you have to walk all the way to the shelves to go and take the book and bring it to your table, that will mean that you will have to pay for that 5 minutes. So that becomes a penalty that is enforced on you due to the amount of time it takes you to get to the shelf and the table, right? Now, let's say you bring a second table as an intermediary, and that table is now between your first table and then the shelves. What this means is, even though it is not exactly where you sit, it has shortened the distance a little. So now on that table, you are going to go to the RAM, to go to your shelves. You will take books and put them on that table. And when needed, you will come to that table and also take the books and bring them to your table. What does this mean? Your penalty for the level 1, that is your table, has now changed from the shelves, which was 5 minutes. It will now change to something shorter relative to the distance of your new table from your old table. So for example, if that distance is just 3 minutes, this will mean that if I get up from my old table and I go to that new table, all I'll have to do is account for that 3 minutes. I do not have to worry about the initial 5 minutes that I was dealing with. But don't forget the amount of time it took you to draw the book from the shelf all the way to the second table. That too affects the average access time in total. So in order to compute the access time, you first need to find out the access time that the second table will have to account for. If we are taking table books from the shelf to that second table, how much time do we spend? We have to get that. That becomes the penalty or the access time for the level 2. And after we get that, we can use that value also as a penalty for the level 1. So then it means this time we are no more directly relying on the RAM. So the RAM is no more our penalty. Since we are relying on level 2 shortens the time, but it still has to pay a penalty. That new penalty on level 2, the access time for level 2, now becomes the penalty in our formula. So if we go back to the questions that we were working right now, this will mean that currently for my level 1, I am at 1 nanoseconds for the hit time. If access time for level 2 is computed to be 35 nanoseconds, then that access time now becomes the penalty in my formula. So it's going to be the hit time for level 1 plus the penalty and the miss rate for level 1 times the access time for level 2, which will now be the penalty. And that will give us the average memory access time. So whenever you are working, only thing you should be looking out for is this. Do I have my miss rates for level 1? Do I have my hit time for level 1? And do I have my average memory access time or my access time for level 2? These 3 values are what you will need for the inclusive multi-level questions. However, if the access time for level 2 has not been given, you will compute that using the average memory access time, but this time solely for level 2. That will mean level 2 hit time plus a bracket of level 2 miss rates times the penalty from the storage that's level 2 references, that is RAM. Yes, Mr. Joshua, it's happening again. You can't hear me.
No, I answered the question. Please, the 35 for the L2 assessment, the access.
Yeah.
Is it that we got the 5 from the level 1 cache?
Yes. We didn't get it from level 1 cache, sorry. No. So, okay, thank you for asking this question. So this makes me see that your problems are deep rooted. Very good. So let's answer that. Right. So as I was saying earlier, right, in order to compute access time in general, we need a hit, right, plus a penalty. We get the penalty when we multiply the miss rates by the penalty from the memory space we are addressing. Is that not correct? So in this case, level 2, it says that the penalty for addressing the RAM is 100 nanoseconds. Since level 2 is dependent on the RAM, then that penalty is what we are going to use in our formula. The formula for calculating the access time for level 2 is the level 2 hit rate, which is given here 5 nanoseconds, plus, and this is the brackets of the level 2 miss rate. So the miss rate has been given down here. So Joshua, follow the pointer. The miss rate for level 2 has been given to be 30%. So that's what you are seeing here. So then the miss penalty is going to be the miss rate for level 2, which is 30% or 0.3, times the access time for the RAM, which will become the penalty and falls on level 2. So when I do the 0.3 times 100, that gives me exactly what? 30. Now I have 30 plus 5, and that gives me 35 nanoseconds. Does that make this clear?
Yes, sir. It's clear now.
Exactly. So that is what the access time is about. But then the access time is for level 2. But remember, we are trying to calculate the average memory access time in total. So we are going to take the access time from level 2, and we'll use that as a penalty for level 1, since level 1 will have to go to level 2. So the time that it will take level 2 to freely give the data to level 1 for it to complete the processing, that time becomes the penalty and falls on level 2 due to level 1, due to level 2's access time. So the formula is now going to be level 1's hit time plus level 1's hit miss rate times level 2's access time. And that is what completes it and gives us the average memory access time. So 1 nanosecond for level 1's hit time, that has been mentioned in the question already. And level 1's miss rate, which is 10%, that you can see down here, times the access time for level 2, which becomes the penalty in this case. And that gives us 0.1 times 35. And what does that give us? So 10 times 35 is 350, jump the point 2 times back, and that's 3.5. And you have 3.5 plus 1, and that gives us the average memory access time of 4.5. So the parameters you should always be looking for is the level 2 access time, your level 1 hit rates, and your level 1 miss rates. If your level 2 access time is not given, look for the RAM's access time, your level 2 miss rates, and your level 2 hit rates, and then you compute them accordingly. So always start by computing level 2. After you get the value, they use it to compute level 1. So we have come to the end of today's session. Sadly, I'd like us to proceed, but actually, my brain, I'm tired. As I said, I was not even supposed to take today's session, so I'm not prepared for it. But thank you for coming. Yeah,
Hello,
Mr. Nyakon.
please, can you take it again for the last time?
Hey, this guy came to kill me. I swear, this guy was
Sorry,
sent to kill
sorry.
me. Okay, I'll take it again for the last time. Perhaps this time, let me use the parameters here. Let me clean these things. Or better still, let me duplicate. All right. There was a big empty space somewhere. Okay, let's use this one. Let's have a good look at what's happening here. All right. I'm going to use illustrations to better explain the concept, okay? Let's draw memory spaces. This is our cache for level 1. Level 1. This is our class for level 2. Let me connect them. So I'm using a visual representation to make this as clear as possible. And then let's say our RAM is all the way over here. All right. Now, as you can clearly see, there's a shorter distance between the level 1 and level 2. Let's say that the distance between level 2 and then the RAM makes it so that whenever level 2 tries to get information from RAM, it spends a lot of time. So let's say the time that RAM will use to give you the data you need fast is exactly 100 nanoseconds. 100 nanoseconds is the amount of time that RAM uses to give you all the data you need. So once data is flowed, it takes 100 nanoseconds for it to get to the level 2. This means when level 2 is trying to get data from the RAM, it spends 100 nanoseconds. That becomes a penalty that RAM enforces for coming to visit him to take data. Once data gets to level 2, let's say the time that it takes for data to travel from level 2 or for level 2 to freely give data to level 1, that time is something like 35 nanoseconds. What will this mean? It will mean that in order for level 1 to get data from level 2, it will also have to spend 35 nanoseconds. That's a penalty. And let's say that penalty is due to the fact that level 2 also has to go to RAM. So it is affected by it. Maybe initially it was meant that level 2 has just an access time of about 2 nanoseconds. But because level 2 has to go all the way to level 1, whenever it misses a data value that it's not having, and because level 2 has to go all the way to RAM, now that 2 nanoseconds are shot up to 35 nanoseconds. What this means is that it affects level 1 in the long run. So it means whenever level 1 visits this place and it is trying to take data from here, it also has to focus, or it also has to, it has to face that 35 nanoseconds time lapse. And after it gets exposed to that, it also slows down level 1 processing. So let's say normally level 1 should have been taking just 1 nanoseconds for processing. But your computer says level 1 is taking 1 nanoseconds, yet at the end of processing, it gives you a different value. That is because it has to account for how much time level 1 takes, how much time level 2 takes, and how much time level RAM will take if each of them is visited. So in order to calculate the average memory access time, I have to take into account the access time for level 1. Now, level 1 doesn't always go to level 2 because there are some data that level 1 holds already. These data values are called the hit values. And the hit values, or the hits, the number of minutes or the amount of time it takes to get to those values that are already on level 1 is called the hit time. Is that clear? So since these values are already held on level 1, the amount of time it takes to get to them is called the hit time. So the hit values are held here. So those values, it takes 1 nanosecond, just 1 nanosecond to get to them. But there are some values that level 1 needs that it doesn't have. And for that reason, since you are using an inclusive system, level 1 visits level 2 to get those values. If those values are on level 2, it's fine. So let's say those values are here. Those values are called misses because level 1 couldn't get them. So it's a level 1 miss. And the level 1 can be found here. Now, because not all the values are missing for level 1, it means it's not all the time that we have to go to level 2. So there is a chance, there is a percentage chance that we might find the data on level 1, but there is also a chance that we will not find it. The chance that we will not find it is called the miss rates. So the chance that the value we are looking for is not on level 1 is called the miss rates. So since that miss rate is possible, it means sometimes we'll have to come to level 2. Is that clear? So now the chance that we will not find the value is called the miss rate. Now, once we are on level 2, we might find what we are looking for. if we found what we are looking for, it only takes us now 2 nanoseconds. Is that clear? But the problem is, if it takes us 2 nanoseconds, that's fine. That's how much time it will take us to read the data to the side. But the problem is sometimes level 2 also has a miss. But not all the values are held on level 2. Some of the values are held in main memory. So if level 2 has data here, and then it also has a miss rate, then it means there is a percentage or there's a chance that level 2 will also have a data not in it. So that chance will become the level 2 miss rate. So the level 2 miss rates. That's the chance that the value you're looking for is not on level 2. Now, if we go to RAM, every data we need is inside RAM. This means RAM has no miss rates. You understand? RAM has no miss rate. There is no miss rate for RAM. So RAM has no miss rates. So whenever we go to RAM, we will get what we are looking for. The only problem is due to the fact that sometimes we have data in level 2 and sometimes we don't, and it means we only have a chance of visiting RAM. So that is the miss rate for level 2. Now, when you come to RAM, before RAM will give you the data in this particular value we've given here, in this particular question, before RAM gives you data, it spends 100 nanoseconds to find the data and give it to you. So then that becomes the RAM access time. That RAM access time will waste the level 2 cache's time. Therefore, it becomes a penalty on level 2 cache. So it means if level 2 wants to access this guy here, then its access time is influenced by it. So in order to find how much time the CPU spends in total when it takes data from level 1, we have to take level 2 and the RAM also into account because we don't know when it will go to level 2. We don't know when it will go to level 1. Now I'm going to take you back a long way. Go to conditional probabilities in statistics. When we're doing conditional probabilities, you realize that when we are calculating the probability, we have to take the probability of it occurring in A and probability of it occurring in B. That gives us the total probability rule, right? In Bayes theorem, that becomes our denominator. And then the top will become the favorable probability we are looking for. A similar concept is being applied here. So in order for us to compute the total memory access time, we have to compute access time for level 2 due to the penalty from this side, the new access time for level 2 due to the penalty here. And we are going to use that value to compute access time for level 1. So in this case, if we know that the miss rate or the chance of missing from level 1 is about 5%, and that's 0.5. And we know that the chance of missing from level 2 is about 0.7%. And in order to calculate the average memory access time, we first start by finding how long it takes level 2 to get data from RAM. That becomes the new access time for level 2. So then we are going to do that by multiplying level 2 hit rates that we have already set to be 2 nanoseconds here. So 2 nanoseconds plus, according to the formula, the miss rate, right, which we have just defined to be 0.7. And then we multiply that by the access time, which will be the penalty on falls on level 2, which is 100. What this gives us is 0.7 times 100 is what? 70 plus 2. And that gives us 72 nanoseconds. What this simply means is if I am coming to access data from level 2, so the 35 years was just a value I gave roughly, okay? So now we found it to be 72 nanoseconds. What this means is that if I am coming to access data from level 2, if that data is not inside it, then there is a chance that I will be spending 72 nanoseconds in total to get that data from level 2, provided it goes to RAM. So then that's the level 2 access time. But this will also mean that initially, level 1 only had to deal with a 2 nanoseconds lapse when it was going to take data from level 2. But due to the fact that level 2 also accesses RAM, now it has to deal with 72 nanoseconds. This now becomes the penalty for level 1. So in order to calculate the average memory access time in total, we already know level 2's own. So we are going to use that to get level 1's value. So the level 1 hit time, that's if the data is on level 1, if it's on level 1. So remember, we are finding an average. An average means for the favorable and the unfavorable in total. So divided by how many chances there are. So then if the data is on level 1, that's 1 nanosecond. Plus, if it is not on level 1, what are the chances that it is not there? According to the question, the chances that it is not there is 50%. So we take that 50% chance, and then we multiply it by the memory speed or the access time for level 2, which we have computed due to the effects of the RAM to be 72 nanoseconds. So 1 plus 72. So we do 0.5 times 72, we get 36. And we combine that 36 with the 1, and that gives us 37 nanoseconds. What does this mean? This means that taking into consideration the values that are actually on level 1, the values that are not on level 1 but are in level 2, and the values that are not in level 2 but are in RAM, putting them together, we can now say that the CPU spends roughly 37 nanoseconds to retrieve data during processing because it has to address all these 3 storage areas. So it spends roughly 37 nanoseconds. And this is only due to the fact that the RAM's penalty has an effect on level 2. Level 2's penalty is also having an effect on level 1. This is done in inclusive systems. In exclusives, you just have to face level 1 and RAM separately, or level 2 and RAM separately. But this is for the inclusive system. So please, is that clear? Mr. Nyako and everyone else, does this demonstration explain it better to you?
Yes, please.
Yes. Yes. Thank you. What about Mr. Joshua, Mr. Phoenix? Does this explanation explain it better to you?
Yeah.
All right. All right.
Yes, sir.
Thank you.
Yes,
So I'm going to drop some questions on your page. Okay, and then you tackle it. And then when we meet next time, perhaps Monday and Tuesday or something, you will let me know what your answers were. Have a great one. And we have gone far into time, 9:23. But it was worth it. Good night, everyone. Sleep and dream. Goodbye.